My name is Thijs Rauman, Hasselplattner Institute, and I present AutoAssembler, a software tool that automatically converts 2D cutting plans to 3D models for laser cutting. This conversion to 3D allows users to make 3D parametric changes very easily, which is crucial for customizing models downloaded from the web. Sharing and reuse is key for any field to mature. However, to make shared laser cut models useful, users need to customize them. For this VR headset to be valuable to users, they may want to change the model so that it fits their prescription, adjust the intraocular distance, reduce the weight, or stretch it vertically so as to allow their phone to fit in. A series of changes that are all trivial to do in 3D, but hard to do in the 2D formats in which these models are currently shared. Assembler Cube, our CHI 2021 paper, is a tool that converts the shared 2D cutting plans to 3D models manually. Users assist the algorithm by puzzling together the model. This means that users need to know about the structure and the parts of the model, which is fine for the current users of laser cutters, but what if the other 99% of people wanted to do this? They are interested in the VR headset and not in the puzzle of assembling it. We therefore present AutoAssembler, a beam search algorithm that automates the process of reconstructing laser cut models. AutoAssembler uses the same import routine as Assembler Cube. Users load the 2D cutting plan into the editor, but now AutoAssembler attempts to assemble the model in the background. Once this is done, users click Import and make the desired modification to the model. Under the hood, AutoAssembler beam searches the space of possible assemblies. It starts with the plate with most joints and then assembles next plates into the model. It scores each of these assemblies based on its heuristic function and picks the 4 best assemblies. It then recursively executes this routine until all plates are assembled into the model. The beam search algorithm makes it tractable for AutoAssembler to track the exponential space of assemblies. Its worst case complexity is O of d times k, in which d is the depth, or the number of plates in the model, and k is the beam width, multiplied by the maximum fan-out. The fan-out are all the possible next combinations at each state, and in our case that is actually proportional to the depth or the other plates that are still in the model. And therefore, the worst case complexity is quadratic in the number of plates. However, AutoAssembler limits this fan-out by only pairing up joints that are candidates to the current state, thereby drastically reducing the typical complexity unless all joints in the model are exactly the same. AutoAssembler achieves this using a data structure that we presented in Assembler Cube, a hash table of the shape of the joints of the model. If we look up a joint on our model, like this green one highlighted here in that hash table, we retrieve the orange collisions in constant time, which are all the joints that fit to the current candidate joint. So the hash table gives us a joint which matches, but there are still many ways to combine the fitting plates into new assembled states. Therefore, AutoAssembler uses a heuristic function that scores these states to decide what assemblies to favor. This function is made up of 6 heuristics, which I will introduce in detail in the next section. AutoAssembler gives preference to compact candidates. AutoAssembler scores compactness by minimizing the size of the bounding box of candidates. This magazine holder, therefore, gets a much worse score than this one. AutoAssembler avoids intersections between plates. It therefore assigns a low score to this train wagon and a much higher score to this one. AutoAssembler gives preference to the use of unambiguous joints. Here, the red plate can be assembled in 12 different ways, and this ambiguity further goes up when assembling the next plate after that. Instead, AutoAssembler assigns a better score to this plate, which has little ambiguity, and then this plate after that. Together, they now constrain what used to be the red plate. AutoAssembler minimizes the number of unmatched joints. Assembling this red plate leads to a strong increase of the search space, as it opens up a lot of new joins. AutoAssembler therefore assigns a better score to this green plate, which closes down 2 joins and opens up only 1, to keep the search space tractable. AutoAssembler prefers to assemble plates that make use of constraints by other plates. Rather than assembling this red nose piece here, which can be assembled in many different ways, AutoAssembler first assembles this green plate here, which is fully constrained by its neighbors, and this plate now in turn constrains the nose piece that we were trying to assemble before to finish off that headset. Finally, we found that most models are symmetric in nature. AutoAssembler therefore assigns a bad score to this plate, which is flipped along the symmetry axis, and assigns a good score to this plate, which is assembled in the correct orientation. To tune the weights of the heuristics, we used hyperparameter optimization based on the 3-Pasen estimator as proposed by Long Wen in 2020. This algorithm converged after feeding around 1000 assembled states as input. Intuitively, we had expected to see a much higher score for intersections here. But the truth is, we aim to save computational resources when scoring plates, as AutoAssembler runs the scoring many times. And therefore we find false positives when looking for intersections, which is why the hyperparameter optimization assigned a lower weight to the truth of the intersection finding. We ran the algorithm on the benchmark of laser-cut models we used to evaluate Assembler Cube. We limited this to the models that have joints at their edges, as AutoAssembler only really works on those. We achieve a success rate of 79% in a fully automated fashion, and by using up to 4 clicks of our manual disambiguation tool, the total success rate goes up to 97%, which we show here at this example of assembling a series of models. So in conclusion, I have been tackling the challenge of how to reconstruct 3D models twice. In my Kayak paper, Assembler Cube, by letting users manually puzzle together a 3D model from 2D plates. And in this paper, I've started to automate that process. What gets me excited about this is that these 3D models now allow others to reproduce and customize the models, resulting in a future where, rather than reinventing models every time, we could really start to build on the work of others and achieve much higher levels of complexity with our laser-cut models. Finally, I want to thank my co-authors at the Hasso-Plattner Institute for a fantastic collaboration on this project. And I look forward to discuss this research with you here in the Q&A or later in my demo session. Thank you so much for your attention.